we can make an excuse to go there for the holidays. We are actually putting this primary mirror together for the Webb Space Telescope right now. It's gonna, I think by the end of January is when this primary mirror is supposed to be finished. So if you come now, you get to see it, which is awesome. There's like an observation deck, and you can watch the engineers in their lab coats like positioning the mirrors. It's so cool. So this is gonna launch later this decade. And this might actually be big enough to do the job if we're lucky, and I'll get into that later, or in a minute. But James Webb was designed its design was completed before we understood all this information about the extrasolar planets. So it doesn't have the capability to block out the starlight. You need both things. You need to be big in aperture to collect enough photons to do the observation, but you also need to block out the starlight. And Webb does not have that capability built in. So what we're working on now, or at least thinking about now at Goddard and a couple other places, is a space telescope dedicated to that will have the starlight suppression capability and also will have the size that you need to get the observation done in a reasonable amount of time. Now I should say, we're going to look at things like James Webb. There's people at JPL that are going to look at things like Hubble that have the starlight suppression into it. How big you get depends on what level of confidence you have in how abundant life is in the universe, or to put it another way, how accurately you want to measure the abundance of life in the universe. So the bigger your telescope, not only do you get a shorter observation of any planet system you're looking at, you also can see deeper into the universe and do the observation for star systems that are further and further away. A bigger telescope basically lets you see dimmer objects. The things that are further away are dimmer on average, and so you get more targets the larger your telescope. You're also integrating less time for each one, so you have more time. You have essentially more time slots for more systems to observe. Now this here's some preliminary yield calculations done by Chris Stark. And if you're somewhere around 4 meters, you might get around 10 planets you observe in the habitable zones of these other stars that are the size that would allow for liquid water oceans. So you might get spectra, some pale blue dot information on about 10 stars if you're about 4 meters in diameter. However, if you're up to about 10 meters, you get about 50. Okay, you get 40 to 50 Earth-sized planets in the habitable zones of these other stars. Now, we are looking at going up to about this regime, this range, and the reason is, if you just do the statistics, if you just do like lottery number type statistics, if you get up to the 30 to 50 observations range, you end up being able to say to a 95% confidence level whether or not there's signs of life on planets on at least 10% of the stars. Okay, so another way of saying that is if we did this mission and we got a handful of worlds, that's not. I'm not going to say that that's not worth doing because I absolutely do think it is worth doing. But if we only got a handful of worlds and we didn't find signs of life on any of them, what would it tell us? We know that, and I'll get to this again later, we know that life is a stochastic process. We know that the things that happened on Earth introduced many things that could have altered the trajectory of life or potentially led to a lack of life on our world. Right? We don't know the extent to which the percentage of planets in the habitable zone that actually have life. That's kind of the whole point of this, is to find out if they do. So if you only have a handful of worlds, you're counting on the ones that you're looking at being the ones that have life. Okay, if it's on less than 10%, you won't see anything. I'm sorry, if it's on fewer than 50% of the planets, you won't see anything. And furthermore, you won't be able to say anything given that lack of information. If you get up to the 30 to 50 range and you do the statistics, you'll at least know that the universe is slow. Because if you get up to this number of observations and you don't find anything, and you do the numbers and the statistics, you can tell yourself, you can conclude that whatever you were looking for was not present on at least 10% of the planets. Okay, and I think that's saying something. Because if you ask me right now, what percentage of planets in the habitable zone have life, and put some error bars on it, I'd say it's somewhere between 0% and 100%. If this mission came back and we didn't get any positive results, I could say it's somewhere between 0% and 10%. Our ignorance would be decreased by an order of magnitude. And if we did find signs of life, then I think that's a successful mission. And we could say how abundant life is to within 10% on those worlds. Okay. So this is hard. It's going to take time. If you want to know the politics of it, I can talk to people about the science politics, not like the red-blue politics. We can talk about that over the reception or over dinner or at conferences or whatever. But I will tell you that I'm a Cubs fan, okay, so I do believe in miracles happening, but when I put my NASA hat on or my NASA jacket or whatever, I don't count on miracles on my day-to-day in the office, right? And at NASA, it's not just our job to come up with a way to make a measurement to test the hypothesis. We have to do it in a way that's not crazy, right? That doesn't require miracles, that we can